Hello, everybody, and thanks for joining today. My name is Nate Drude. I'm an R&D and technical sales engineer at Variscite. Today, I'll be presenting how to get started debugging firmware on the Cortex-M coprocessors on Variscite System on modules. This is our agenda for today. I'll start by giving an introduction to Variscite. Then I'll give an introduction to the Cortex-M coprocessors. We'll review a previous webinar where we presented how to get started debugging C and C++ applications using VS Code. And then we'll walk through a demonstration debugging, showing how to debug Cortex-M coprocessor firmware using VS Code. We'll start by how to set up the hardware. Then we'll look at setting up the host computer. We'll create a new project within VS Code, and then we'll run that project using the debugger. I'll finish by looking at some next steps, and then I'll do my best to answer any questions that you have. All right, about Variscite. Variscite is a leading system on module provider. We've been in the market for over 19 years and have built an extensive global customer base and pipeline. Variscite provides a stable supply by using our internal production facilities, giving us complete control over the manufacturing process. Variscite's hardware and software R&D team provide direct support to our customers, usually within 24 hours. Variscite is the only system on module vendor as part of NXP's Platinum membership. We provide the most diversified and scalable i.MX8 product portfolio. Variscite has the highest quality standards, meeting strict regulatory requirements, including medical standards. And finally, Variscite has an ecosystem of partners that in the end allow us to provide a complete end-to-end solution to our customers. So why should you use a Variscite system on module? Here's some of the advantages. Using a Variscite SOM provides a faster time to market. Using a SOM allows you to minimize your hardware and software development and testing phases. It enables reduced R&D costs. You can avoid the high cost and risk of hiring a design team and instead take advantage of Variscite's expertise in the complexities of SOM design and layout, both on the hardware and software sides. Scalability. Variscite has several SOM families supporting many SoCs that allow for seamless scalability for current or future products and technologies. 100% yield all the time. You'll receive fully functional modules from Variscite. No need to manage the complexities of manufacturing and testing yourself. Variscite's hardware and software is production ready. We have BSP and driver support for multiple operating systems such as Yocto, Ubuntu, Debian, and Android. The hardware and software is tested by Variscite and used by Variscite's large community of customers. Variscite provides free technical support for both hardware and software, again, allowing direct access to our R&D engineers using the customer support portal. All of our software is open source on GitHub, and we provide access to CAD files. And we also have helpful guides and documentation on our software wiki. Our in-house production enables stable availability and lead times, and we have up to 15 years of longevity, so you can rest assured that you'll have long-term support from Variscite. Variscite has two scalable SOM families. One is named the VAR SOM, and the second is named the Dart family. On the top, you can see the VAR SOM modules, which offer scalability from the i.MX6UL all the way up to the newest i.MX8M Plus. In general, these are all pin-to-pin compatible with each other. And the Dart family on the bottom has a smaller form factor, but actually provides more interfaces than the SOM family. It's also pin-to-pin scalable within its own family and supports scaling from the 8M Mini to the 8M Plus. These two families provide scalability and processing capabilities while maintaining the same interfaces and form factor, allowing you to scale from the Cortex A7 and A9 all the way up to the A53 and A72, depending on your product requirements. And as I mentioned, Variscite also has a software wiki. On the software wiki, you'll find documentation that is specific to your SOM and the software release that you're using. We have developer guides for Yocto, Android, Ubuntu, Debian, and FreeRTOS. We have how-to guides that show how to use the hardware interfaces like GPIO, UARTs, Wi-Fi, Ethernet, etc. There's a link to Variscite's customer support portal. And we also have a MCUXpresso development with VS Code guide, where you'll find much of the documentation from this webinar. So you can visit Variscite's wiki at variwiki.com. You can select your SOM and then select your software release, and then you can see all the guides that are specific to that SOM and software release. And as I mentioned on the previous slide, we also have guides on our wiki for getting started with Cortex-M development. The image on the left shows our Getting Started guide, which walks through how to get the source code, how to build it, and run the demos from either Ubuntu or Linux. The Getting Started guide has a section that links to NXP's documentation for getting started using IAR Embedded Workbench. As an alternative to IAR Embedded Workbench, there's a section that introduces developing with Microsoft VS Code, and a link to a full guide on the right, which walks through the whole process to get started with VS Code. And again, most of the content from this webinar is derived from these guides, so if you need more information, you can visit them after the webinar. Okay, next I'll give an introduction to the Cortex-M coprocessors. All Variscite i.MX8 SOMs have at least one Cortex-M4 or M7 coprocessor. For example, the i.MX8M Plus SoC has up to 4 Cortex-A53 cores, which typically run some version of Android or Linux, and a single Cortex-M7 coprocessor. In this webinar, we'll be focusing on using Microsoft VS Code to debug firmware on the Cortex-M7 for the i.MX8M Plus family. Generally speaking, the A53 cores, which are shown on the left, are used to run an operating system like Android or Linux. The Cortex-M7, shown on the right, is useful for applications that require real-time control or data acquisition, low latency, or deterministic operation. An example might be phase-fired control of a triac, or some motor control algorithm, or maybe reading a sensor at a very precise interval. A very common use case is to run a touchscreen display using Linux on the A53, and then run a real-time application on the M7 that does the actual system control logic. It's possible to communicate between Linux and the Cortex-M7 by using the remote processor communication bus, or RP message. RP message is a VirtIO-based messaging bus, which allows kernel drivers to provide shared memory and communication with remote processors available on the system. To summarize, Linux and Android have some limitations for real-time applications. So the Cortex-M7 on the 8M Plus allows you to offload real-time control or processing to a dedicated processor. As I mentioned, all Variscite i.MX8 SOMs have at least one Cortex-M4 or M7 coprocessor. The VAR SOM MX8 and Spear MX8 actually have dual Cortex-M4 coprocessors. And all the others have a single M4 or M7 coprocessor. In this webinar, we'll be focusing on the VAR SOM MX8M Plus. However, the process is generally the same for all other SOMs. Regarding software support, Variscite provides a GitHub repository, which is based on NXP's MCUXpresso SDK. The repository contains example projects for each of Variscite's SOMs. Each project is created by NXP for NXP's evaluation kits and then ported by Variscite for Variscite's kits. As you can see here, there are examples for a Hello World project, which is a very good place to start. There are driver examples that'll show you how to use things like I2C and UART devices from the firmware. There's a multi-core examples directory, which shows examples for communication between the A53 and M7. And there's also a directory with examples for FreeRTOS projects. Okay, so before we dig into debugging, just to help add some context and wrap our head around kind of the big picture, let's first look at the process for getting started with the Cortex-M firmware. So the process is to first install the toolchain and SDK on your computer, and then build and install the Cortex-M firmware. Then you need to configure a Linux device tree with Cortex-M support. And then finally, we can load the Cortex-M firmware either from Ubuntu or Linux. So again, to help us wrap our head around this, let's walk through a quick example of how to build and run firmware on the Variscite MX8M+. Okay, in the next slides, we'll walk through a brief example to build the Cortex-M firmware, configure the Variscite MX8M+ to boot a dedicated M7 device tree, and then we'll run a demo from Linux. On the hardware side, we have a Variscite MX8M+ with 2 serial ports. The serial port on the left, UART2, is connected to the A53 Linux console, and the serial port on the right, UART4, is connected to the Cortex-M7. When we run the M7 firmware, we'll see Hello World printed on the console on the right. So let's walk through these steps in the following slides. So to get started, we first need to install the toolchain and SDK. So first we can create a new project directory named var MCUXpresso. You can name this anything you want. This is just an example. Then we need to install the toolchain for cross-compiling the firmware. Basically, you just fetch this from the ARM website and unpack it. Next, we'll use Git to clone the MCUXpresso SDK from Variscite's GitHub repository. Again, this SDK provides example projects that were created by NXP and then ported by Variscite. So in the end, we should have a project directory that contains FreeRTOS Variscite and the ARM toolchain. The next step is to build the firmware. Later in the presentation, we'll set up Microsoft.vscode to build the firmware. But for now, let's build it from the command line using scripts that were provided by NXP and Variscite. So to build the Hello World demo, we need to first change directory to the Hello World project for the Variscite MX8M+. Then we need to export an environment variable, ARM GCC dir, to tell the compiler tell the makefile where the compiler is. Then we need to run the build all script. And after we do this, we'll see that hello world.bin and hello world.elf are generated. Next, we need to install hello world.elf on the /lib/firmware directory on the target device. In this example, we'll use SCP to transfer the file, but you can also do this using a different method, like using a USB or SD card. Before we can run the Cortex-M7 firmware, we first need to boot a special Linux device tree file. The device tree file must disable any peripherals that will be allocated to the Cortex-M7 to avoid any conflicts. The A53 and M7 cores cannot both access a peripheral at the same time. So first we'll configure uboot to load a dedicated device tree with Cortex-M7 support. We can use the fwsetenvironment command to set the uboot environment variable fdt file to i.MX8 var som symphony m7.dtb. And then we can reboot to use this new device tree file. Basically, this device tree file, again, just disables any devices that are used by the M7. So in this example, we have UART4 being used by the M7, so we disable that in the device tree. And then the code snippet on the bottom just shows the initialization code for UART4 in the M7 firmware. Okay, after building the M7 firmware, installing the hello world.elf on the 8M+, booting a dedicated device tree, let's look at how to run the Hello World demo from Linux. Here in this picture on the left, we have the UART2 Linux console connected to the A53, and on the right, we have UART4 connected to the M7. So to load and run the firmware, we can use the Linux remote processor framework. To do this, we change directory to the /sys class remoteproc0 directory. We can load the firmware by writing hello world.elf to the firmware file. We can start the firmware by writing start to the state file, and we can restart the firmware by writing stop and then start again to the state file. And each time we run start, we can see that hello world is printed on the Cortex-M7 console on the right. We'll look at this in more detail later as we look at how to debug firmware using Microsoft.vscode. Okay, now that we've briefly talked about how to run firmware on the Cortex-M cores, let's back up and look at the Microsoft Visual Studio Code. We recently did a webinar showing how to debug using C and C++ applications using VS Code. Many of the same principles apply to debugging the Cortex-M coprocessors. So let's review some of this content. Okay, a quick introduction to Microsoft Visual Studio Code. VS Code is a modern cross-platform source code editor. It's lightweight and very easy to install, but it has all the features you'd expect. Personally, I've been using VS Code for several years now to do most of my development. It supports most programming languages such as C, C++, Node.js, Python. It supports graphical, local, and remote debugging. You can install extensions to add support for additional software languages, debuggers, or tools such as lint. The project configurations for the toolchain, debugging, and other features are all saved within the project. So this means they can be captured by revision control tools like Git, and then easily reproduced by both yourself and other engineers on your team. Another nice feature of VS Code is IntelliSense. IntelliSense enables features like code completion and the ability to easily navigate between source code files and functions. VS Code also has an integrated terminal. So this allows you to open up a terminal without leaving VS Code to connect to another device, maybe via SSH or opening up a serial console. And then finally, in my opinion, the most powerful feature of VS Code is the ability to do remote development. By using an SSH connection to a remote computer or server, VS Code allows you to develop and debug software as if you were working natively on that computer. So this is really helpful if you work on a laptop but have a more powerful server for compiling your software. This is an overview of what we did in the previous webinar. At a high level, we had a development computer running Ubuntu 20 and VS Code, and connected to Variscite's i.MX8 mini evaluation kit running Yocto Hardknot. We used VS Code to create a new C project. We configured a cross compiler. We built the project, deployed the application to the target device, and then debugged it graphically using VS Code. The hardware setup and process for debugging the Cortex-M coprocessor is very similar, and we'll walk through this in several slides. In the previous webinar, we also demonstrated a neat feature about Microsoft VS Code. Again, it supports remote development using SSH. So basically, this allows you to use your Windows or Apple-based laptop for code editing while using the resources and SDK available on a more powerful Linux build machine. To summarize this feature, basically any Windows, Ubuntu, or Apple computer can connect to a Ubuntu machine running using SSH. And then VS Code will behave as if it's running natively on that development machine. So looking at this picture, again, we have the Variscite MX8 Mini on the right. It's connected to our build server in the middle, which is running Ubuntu 20, and has the Yocto SDK and source code and all the other dependencies for building. And then on the very left, we can connect to the build server using, for example, a Windows computer. And when we do this, VS Code will open a new perspective and behave as if it's running native on the build server. So this means we can edit, compile, and even debug applications remotely from any operating system that supports VS Code and use the resources and SDK on the build server to compile the application. So again, this is a neat feature to use, especially if you use a Windows or Apple laptop. And this concept is still true when debugging the Cortex-M coprocessor. So if you want to learn more about this, you can go to our wiki, or you can view the previous webinar about debugging with VS Code where we walk through this in more detail. And finally, the last thing we'll review about the previous webinar is the project that we created. I show you this just because we're going to follow a very similar process today, so you might find it helpful to go back and review. We created a very basic project. It was a Hello World project. We made a main.c++ source code file that simply printed Hello World, and it allowed us to do some debugging. We created a make file to cross-compile the source code. We created a var deploy GDB script that builds, deploys, and launches GDB server on the target. And then we created 4 VS Code configuration files. We created settings.json, which allows us to set up global environment variables for the SDK and project. We created tasks.json. Tasks.json allows us to override VS Code's built-in tasks for compiling, building, and debugging the project. We created CPP properties.json, which basically just sets up the include path for IntelliSense. And then finally, we made launch.json, which is used to configure VS Code for debugging. So again, as we move forward through this presentation, you'll see some similarities between debugging a Linux, C, and C++ application and debugging firmware on the Cortex-M7 coprocessor. All right, so now let's walk through the process of debugging the Cortex-M coprocessor firmware using VS Code. And we'll start by looking at the hardware setup. Okay, this is the hardware setup that we'll be using today. We have a laptop running Ubuntu 20 in VS Code and Variscite's VAR-SOM MX8M Plus evaluation kit running Yocto HardNot. We'll use USB to connect to a Segger J-Link debugger and use the JTAG header on the VAR-SOM MX8M Plus. We will also connect to UART4 on J18 pins 7 and 9. This will allow us to see some output from the firmware, like the example that we showed earlier. Then later we'll walk through the steps to configure a development environment after a fresh installation of Ubuntu 20.04. Using VS Code, we'll then create a new C project, configure the cross compiler, compile the project, and debug it using VS Code's graphical debugger. I want to also point out that Segger also offers Wi-Fi and Ethernet versions of the J-Link. So instead of using USB, you can also connect using Wi-Fi or Ethernet. It's just a small change in one of the configuration files, and I'll show how to do that later. The nice thing about this is it provides electrical isolation, and it allows you to debug the product without being physically connected to it. Okay, and as we mentioned earlier, when setting up our hardware, we need to configure the Linux device tree to avoid any conflicts between the A53 and M7. So for example, we can't use UART4 in Linux and on the A53 and in the M7 firmware at the same time. Variscite provides an example Linux device tree that supports our Cortex-M firmware projects for each of our SOMs. In the example here, we use, again, the FW set environment utility to set the U-boot environment variable FTT file to i.MX8 plus var som symphony m7.dtb. Then we reboot the device to use this device tree file. And again, this device tree file is simply just disabling the devices in Linux that we plan to use in the Cortex-M7. So in the code snippet here, you can see we disable UART4. Other examples use SBI2, so it's also disabled. But in the end, customers should modify and create a new M7 device tree that's specific to their application. After setting up our hardware and configuring the 8M Plus evaluation kit to boot the correct device tree, now let's look at how to set up our host computer. To set up the host computer, there's just a few steps you need to follow. This webinar assumes Ubuntu version 20.04 is installed. In general, other Ubuntu versions or distributions will work, but may have slightly steps or configurations to get started. So after a fresh Ubuntu installation, you need to install VS Code and several VS Code extensions. Then you need to install the MCUXpresso toolchain and SDK like we did earlier. And finally, we need to install a Segger J-Link package for debugging. So next I'll walk through each of these steps. I'll skip over installing Ubuntu 20.04. We'll just assume that we're starting from a fresh installation. So after a fresh Ubuntu installation, the first thing to do is to install Ubuntu 20.04 dependencies. So we need to install things like Build Essential, GDB, Git, and CMake. After this, we can install VS Code in a single line by using Ubuntu snap. So we can just run sudo snap install code. That will install VS Code. And then finally, we can install several VS Code extensions for C++, Cortex, debugging, and assembly syntax support. This can be done either from the command line as shown on the bottom left or from VS Code graphically as shown on the bottom right. Okay, the next step is to create a new project directory named var MCUXpresso. And again, you can name this anything that you prefer. Then we need to install the toolchain for cross-compiling the firmware. Basically, you just fetch this from the ARM website and unpack it. Next, we use Git to clone the MCUXpresso SDK from Variscite's GitHub repository. The SDK provides example projects, again, that were developed by NXP and then ported by Variscite. After this, in the end, we should have a project directory called var MCUXpresso that contains our FreeRTOS projects and our Arm toolchain. Okay, after installing the toolchain and SDK, the next step is to install the Segger J-Link package. This package is required to use the USB J-Link debugger. Since you have to accept Segger's license, you'll need to follow the link here or on our wiki using a web browser to download it. And then after downloading it, you can manually install the Debian package as shown by the example here. After this, it will install a directory in the /opt Segger directory, which will we will later configure inside VS Code to tell VS Code where the debugger package is. And then lastly, there's a patch from NXP that needs to be applied to support the 8M Plus. Again, this patch has to be directly downloaded from NXP after accepting NXP's license agreement. So after downloading this, you can unzip the archive and then unzip the jlink.zip archive, and then finally copy the J-Link script for the 8M Plus to the /opt Segger J-Link directory as shown here. Again, this is only needed for the 8M Plus platform. All other Variscite SOMs are supported directly by Segger's Debian package. Okay, finally, after setting up our hardware and development computer with VS Code and installing the toolchain and SDK, we're ready to create a new project and open VS Code. So in this section, I'll introduce again some of the example firmware projects, and then we'll walk through how to configure VS Code to edit and compile the project. When creating a new project, in my opinion, it's always best to start from a known working example. As a reminder, NXP creates the MCUXpresso SDK, which has examples from NXP evaluation kits, and then Variscite ports these projects to run on Variscite evaluation kits. Here we have a screenshot of some of the examples for the VAR SOM MX8M Plus, but there are also similar projects for all of our i.MX8 SOMs. As I mentioned previously, there are examples for drivers like I2C and SPI. There are multi-core examples that demonstrate communication between the A53 and M7. And there are also examples for using FreeRTOS as a firmware project. For this webinar, we're going to focus on the Hello World example. As you can see in the code snippet here at the bottom, it's a simple project that will initialize the M7, initialize the UART, and then print Hello World. And then finally, it will enter an infinite loop and basically just echo all of the characters that it receives. Okay, the Hello World project can be compiled directly from the command line. We looked at an example for how to do this early in the presentation. And it can this process is also documented on Variscite's wiki. If we want to compile and debug the project using VS Code, we need to create some configuration files inside a directory named .vscode. The table here shows all of the files that are necessary to create, as well as a short description for their purpose. The first file is a .svd file or a system view description file for debugging. This provides the Cortex-M7 registers and addresses to VS Code and Segger J-Link. We need to create a settings.json file. This, again, just has global environment variables that will be used by the SDK as well as the project. There's a tasks.json file. We use this file to override and extend VS Code's built-in tasks for building and cleaning projects. There's a cpp properties.json file. We basically just use this to configure the include paths for IntelliSense. And then finally, we create launch.json, which is used to configure the VS Code debugger to configure the Segger J-Link debugger within VS Code. To help save time, Variscite provides a script to generate all of these files for each of our example projects, and we'll look at how to use that on the next slide. Okay, to help create the .vscode configuration files for compiling and debugging, Variscite provides a script called var add vscode support.sh. To use this script, you just need to pass the board, which for us is SOM_MX8MP, the project path, we'll use the Hello World one, the target memory, either DDR or TCM, and a path to the Segger J-Link installation. So after running this command, we can see below that the .vscode directory is created in the Hello World project folder. In the next slides, we'll look at each of these files and highlight some of the relevant or interesting content. After choosing the Hello World example project and then creating the .vscode directory contents, we're now ready to open VS Code. The easiest way to open VS Code is to launch it from the command line and pass a path to the Hello World project. You can also open it from the Ubuntu application launcher. So after opening VS Code, it should look something like this. On the top left, we see the .vscode files that we generated, and on the bottom left, we see the Hello World example project from Variscite. Again, in the next slides, we'll review each of the .vscode configuration files, as well as the hello world.c file. Okay, first we'll look at settings.json. As a reminder, settings.json basically just contains global variables for the SDK, the project, and the target device. And these will be used inside of the other configuration files. So here we define the SDK installation for the ARM compiler. We define the J-Link installation directory and several include paths for the C++ and IntelliSense parser. In the C CPP properties.json file, we configure the include paths for VS Code and IntelliSense. These are the variables that we defined in the previous slide. Just as a reminder, IntelliSense is just a feature of VS Code that allows you to easily highlight and navigate source code by following function definitions or variable definitions, things like that. Next, we'll look at tasks.json. This file allows us to override or extend VS Code's tasks, such as building and cleaning. Each example project from NXP and Variscite comes with scripts to build and clean the project. Tasks.json simply just defines a build and clean task and configures them to run the existing scripts. So when we run the clean or build VS Code tasks, either using the user interface or keyboard shortcuts, VS Code will run these scripts. And later when I walk through a demo, we'll see how to run the build task. And then finally, launch.json. We use launch.json to configure VS Code for debugging. It's a pretty big file, so I don't want to go through every single line, but I'll highlight some of the important ones. For more information, Microsoft has a website with documentation defining all of the properties for each of the JSON files that we looked at. First, on line 8, you can see we are using the Cortex debug extension. When we installed VS Code, we also installed this extension, which allows debugging ARM Cortex processors from within VS Code. Next, on line 11, there's an IP address property that is commented out. If you're using a J-Link, Wi-Fi, or Ethernet adapter, a debugger, you can set this property to the IP address of your debugger, and then you can debug without using a USB cable. And then below this, you can see the properties that configure the locations of the toolchain, the J-Link script for the i.MX8 Plus SoC, as well as the SVD file for the SoC. All right, next, let's walk through how to run the project using the VS Code debugger. Now that we have our hardware all set up and we created a new project with the necessary VS Code configuration files, we're ready to debug the Hello World project. As you can see here, this is a really simple project. Basically, it just initializes the memory, the clocks, and the UART4 peripheral, and then prints Hello World. And then it enters an infinite loop where it prints all of the characters that it receives. It's a very basic project, but the debugging process is the same for larger and more complex projects. Before debugging, let's quickly review the hardware setup. At a high level, we have a development computer on the left running the Ubuntu 20 and VS Code. And we have Variscite's VARSOM MX8 Plus evaluation kit running Yocto HardNode on the right. We're using a USB J-Link debugger that's connected to the i.MX8 Plus JTAG connector. And we also have a serial cable connected to UART4 on J18 pins 7 and 9. One last thing to do before we start debugging is to open a terminal and connect to the Cortex-M7 serial ports so that we can monitor the output. We can do this all directly from within VS Code. So as the animation shows here, we can open a new terminal in VS Code, and then we can start Minicom passing the appropriate arguments for the USB device and baud rate. So to open a new terminal, we can select terminal and then new terminal. Then we can run sudo minicom -d and pass it the serial port device. And then we can run -b, passing in the baud rate. After this, the only thing we need to do is go to the serial port setup and disable the hardware flow control. And after we do this, assuming you're connected to the right pins on the 8M Plus evaluation kit, we'll be able to see all of the output that is printed by the Cortex-M7 firmware. And finally, we're ready to start debugging. This animation here shows the process of setting breakpoints, building the project, starting the debugger, using the GUI to step over lines of code and inspect a variable. So we'll walk through this animation here twice. We can run start, we can go to the run menu and then run start debugging. This will take just a moment. After this finishes, we can use the GUI to step over lines of code like a normal debugger, or we can hit run to run. We'll open up the serial port connected to the M7, and when we click run, we'll see that hello world is printed. So now we're sitting inside of this infinite loop, and as we type inside of the serial port, we can see that it's echoing back everything that we type. We can set a breakpoint on line 52 and inspect the CH variable. So we set a breakpoint, and then I'll type the letter H here, and we can see that the breakpoint is triggered. We can add a watch on the CH variable and inspect it and see that it's indeed set to the character H. Click run, and we'll do this one more time. We'll type in P this time. We can inspect and see that it received the P character. Then we can stop the debugger. Walking through this one more time, we'll set a few breakpoints here graphically on the left on lines 38 and 47. Then we can run terminal run build task. And when we run build, we'll see that the firmware is built. This is running the tasks that we configured in tasks.json. Then we can run start debugging, or type F5 on the keyboard, which will start the debugger. Again, it takes just a few seconds to load. After this, we can use the interface to step over different lines of code. We can select run to just simply run. Open up the serial port here. When we step over the hello world line, we can see that hello world is printed. Again, we're inside the infinite loop here, and it's echoing back what we type. Set a breakpoint on line 52 so that we can inspect the CH variable. And then we'll type the character H into the console. We can see it triggers a breakpoint. We can add a new watch on this variable and see that it received the character H. And we'll do that one more time. We'll type in the character P, see it triggers the breakpoint again, and we can inspect that character. So this is just a very basic Hello World project, but the principles are all the same for more complicated or larger projects. So let's move forward and look at the next steps. Okay, so we'll finish by looking at some next steps here, and then I'll do my best to answer any questions that you may have. Okay, so as I mentioned, we have a full guide on our wiki for getting started developing with VS Code. So you can go to veryWiki.com. If you're using the plus, you can select var sum MX8M plus, click on MCUXpresso 2.10, and then click on the developer's guide. Also, you can go to our GitHub repository for the 8M Plus or any of our SOMs and look at the example projects. So we just looked at the Hello World project, but there's probably one that's closer, more closely aligned to your end application, maybe using something like SPI or I2C. So you can experiment with those projects and try to find the best one to use as a foundation for your new application. All right, here we are at the time for questions. So I'm going to switch views here, and I'll see if I can answer any questions that you may have. Okay, so the first question is it possible to use the same pin on the Cortex-M and in Linux? So no, it is not. It's not possible to share the same resource from within Linux on the A53 and the Cortex-M firmware. The resource needs to be disabled on either side. So if you're going to use it inside the Cortex-M processor, you need to disable it on the Linux side. If you're using a GPIO pin, the one thing to know is that you should disable the entire GPIO bus on the Linux side. So when you're designing your hardware, you should allocate the GPIO pins in a way such that the ones you want to use from Linux are on one bus and the Cortex-M firmware on another bus. Next question is, does the build server, it just moved on me here. Does the build server require graphics display abilities for the remote development work? No, the build server does not require a display. You can just install a Ubuntu 20 server instance if that's what you prefer, if you don't need a display. You can even do this just within a virtual machine on your computer if that's easy enough as well. But no, basically you just need any Ubuntu installation and then follow the same dependencies and process for installing everything that we followed in this webinar. And as long as it has a USB connection to the Segger J-Link or a Ethernet or Wi-Fi connection, it should work without a display. Does the debugging work with the J-Link base version? I'm actually not familiar enough with each of the J-Link devices. On the J-Link website, there is a table that shows the compatibility with the various J-Link debuggers. So I'm not sure offhand right now, but you can go to the J-Link website to see that, or feel free to open up a ticket within our customer support portal and we can research that. If we use VS Code or Eclipse to cross-compile on the PC, do we still need a build server running in the Linux environment? Solution requires each developer to own 2 computers. Actually, you can have so I'll answer this kind of in 2 parts. You don't actually need 2 computers. So you could have 2 developers, each with their own Windows laptop, for example, and a single Linux server somewhere, as long as they both have access to it, and you can connect to it remotely and build that way. I suppose if you're debugging using a USB connector, probably only one can use that at a time, but yeah, in general, multiple people can use the build server at the same time. And Variscite tests build-in from VS Code using a Ubuntu environment. I believe using the IAR embedded workbench, you can build from within Windows. I'm not 100% sure on that. It's not a configuration that Variscite has tested. Another question is, why is it necessary to have a dedicated device tree file for the M7? You don't actually need a dedicated device tree file for the M7. Variscite has separate device tree files because our Wiki explains or supports using different hardware interfaces for both Linux or the M4. But basically in your product, you again need to disable the interfaces either in on the Linux side or on the Cortex-M side so that they're not both allocated at the same time. Is there a preference in the Yocto version being used when performing this debugging environment for stability and maturity for a product? Each of our Yocto release notes pages will have a row in the release notes that basically shows which Cortex-M features are supported. As far as I'm aware, all of the latest releases support the Cortex-M7 firmware. So if I were to recommend getting started right now, I would probably use the latest Yocto version from Variscite for the SOM that you're using. Is this example code available in GitHub? Yes, all of the example projects are available in our GitHub FreeRTOS Variscite repository. So it's github.com/varigit/FreeRTOS Variscite, I believe is the path. Can we debug without J-Link? You can run the firmware without J-Link. So the first example that we walked through early on in the presentation where we built it from the command line without using VS Code, you can, and then we ran the firmware using the remote proc, Linux remote proc framework. You could do that, and I suppose you could debug kind of using printfs or some GPIO pins or something of that nature. To actually debug and use breakpoints, to my knowledge, you have to use a J-Link. One of the questions is, when using FreeRTOS on the M7, how does the communication work to the Linux side to the A53? There are several example projects within the FreeRTOS Variscite repository that you can look at underneath the multicores directory. The most simple one basically exposes a communication bus to the Linux side by using a serial port driver. So there's a Linux driver that manages the RP message interface to the between the Cortex-M7 and the A53, and then it exposes that interface to user space using like a /dev/t2i RP message device. And so on the Linux side, if you follow this approach, on the Linux side, you can write an application that sends data through that serial port, and then you'll receive it on the M7 side, and you can also respond from the M7 and send it to the A53. So on the Linux side, it basically looks like a serial interface. On the M4 side, there's an API inside of the example that you can use to get started. So again, go to the examples directory, look at the multi-core examples. It's something like string echo T2I example or something like that. I see one question that says, if you send roughly 128 bytes, how long will that take? I'm assuming you're talking about using the remote messaging interface between the A53 and M4. I don't know this information offhand, but I just recently Variscite posted a blog post on asymmetric multi-core processing, and there was some research done on the latency for the communication between the A53 and M7 interfaces. So I suggest you look at that blog post and review that. I think there's some information that you'll find helpful there. Can you update the C code from within Linux without using the J-Link? So I think, yeah, similar to the example that we started when we started the presentation, the very first example I did where we built the C code and then we sent it to the Linux device using SCP, and then we use the remote proc framework to start and stop that firmware. That's how you would do that. So you can start it and stop it anytime from within Linux, and you can reload it by writing the file to the file name, the firmware file name, to the firmware file within the remote proc directory. Is there information for configuring VS Code on a Windows environment? Again, the building and debugging is only tested and supported from Ubuntu, but you could run a Ubuntu virtual machine or a Ubuntu server that's physically connected to the J-Link device, and then run VS Code on any computer, Apple computer, Windows computer. There's instructions on our wiki for how to do that remote development, and also our previous webinar goes through kind of step-by-step for how to connect using a Windows computer. Is there shared memory among Cortex-M and Linux? This shared memory so the communication is all done through this remote messaging framework. The shared memory, I think, would have to be configured within the Linux driver. There's Linux driver examples for the two remote processor communication examples. So inside the FreeRTOS Variscite, there's the multi-core examples. There's several examples in that directory, and there are drivers that are aligned to those examples inside the Linux kernel. And so the Linux driver would be responsible for managing that shared memory. Why VS Code and not Eclipse for debugging? I suppose it's possible to configure the cross compiler with an Eclipse. I'm not familiar with it enough right now to know how to configure the debugger, but certainly you can configure Eclipse for cross compiling. So VS Code is just the example that Variscite has put together. But yeah, I'm sure you can use Eclipse if this is your preference. All right, well, I see there's some other questions here that are a little bit more technical. I think this is all we're going to get to right now. I suggest for some of these questions that you would go to the Variscite customer support portal and open up a new ticket, and our R&D team, including myself, will be happy to help you there. Okay, so you can contact us at our website, so feel free to head over to variscite.com to look at all of our products. You can contact our sales team by email at sales@variscite.com. You can visit our customer support portal for any technical support for both our hardware and software teams. We have our varywiki.com for our software guides, and you can go to github.com/varigit to see all of our open source software, including all of the firmware that we presented today. So I thank you for joining this webinar. I hope it was helpful to you, and I look forward to seeing you next time.